lesson, we'll introduce two very important measures of bond risk management, that is duration and convexity. First, we'll discuss the relationship between bond prices and interest rates. Next, we'll compare maturity with duration with a simple example. We'll also discuss the duration of a bond as a measure of its sensitivity to interest rate changes. We'll also discuss a simple proof of duration measure. Next, we'll discuss duration as price value of basis points, that is PVBP measure, and factors affecting duration measure. Then we'll discuss the convexity correction and a simple exposition on convexity. Finally, we'll discuss bond portfolio management and the role of duration and convexity in various bond portfolio management strategies. In this video, we'll introduce the sensitivity of bond prices to interest rate changes and also its application to risk management in bond portfolios. Let us compare the cash flows and the impact of interest rates on two different maturity bonds. One is 30-year bond, one is 3-year bond. The cash flow discounting makes it quite obvious that rising interest rate would result in fall in values of these bonds. Both of these bonds offer 4.875% coupon. Now, please note a very interesting pattern emerges when you observe these cash flows. You can see that the impact of changes in interest rate is rather more drastic on this 30-year bond. You can see decline is quite sharp as compared to 3-year bond, which seems to be rather less sensitive to changes in interest rates. The reason is quite simple. The impact of changes in interest rate is rather more drastic on 30-year bond cash flows, those that are coming in distant future, particularly the principal payment, which is a major component of cash flows, while that on 3-year bond is much less because of the power of compounding. So you have compounding up till only power of 3. On 3-year bond, principal is discounted at 3-year discount rate, while 30-year bond is hit by the power of compounding even for more than 25 years, like 30 years, 29 year, 27 year, and so on. So the impact of interest rate change is rather more sharp on 30-year bond. One interesting point to observe here that when the interest rate is same as coupon 4.875, both these curves cross each other. That means at this point the prices are same, which is same as the par value or face value of 1000 rupees. But other than that, we can notice the sharp fall or decline in the value of 30-year bond as compared to 3-year bond. This idea that interest rate changes result in bond price changes is very useful and important and has applications in risk management. For example, one would like to know if interest rate change, how much there will be a change in bond price. And this search for changes in bond price takes us to Taylor series expansion. A Taylor series is a serial expansion of a function about a point, and more specifically, it's an expansion of a continuous function fx. For example, if you're looking at changes in value of function around a, for example, fa, then fx, the value would be for small changes would be fa plus f dash a into x minus a plus f double dash. This is double derivative, this is first derivative, and so on. Now, you may ignore the higher order changes. Generally, interest rate changes are not as drastic. They may be small changes. If in India you have RBI changing interest rate by 25 basis point, like 0.25% or 50 basis points, so it may not be a very big change. Otherwise, it may destabilize markets. So one can do well by ignoring the higher order terms and keep only up till 2 order, where H is the small change in interest rate from its level I. So H is the change in interest rate, or you can also call it DI or D1 plus I. Later we'll see what is the significance of this. What is the significance of this D1 plus I, changes in 1 plus I, but mathematically changes in I or 1 plus I are same, which is H here. And we ignore the higher order terms. Another interesting part is if the changes are even smaller, then you can even ignore the second order term and keep this first order term. Now that kind of approximation is often related to duration measure, which we'll see later. But important to note that actual changes are like this. When you are ignoring the second order term, your prediction would be something like straight line slope. This P dash I is the slope in the price function. So the slope multiplied by delta change in yield or interest rate H can give you reasonable approximation if you are operating over a very small range like this. However, when you are operating over a larger ranges, bigger changes in interest rate, then you need to consider this convexity aspect. Why this gap is appearing? Because of the convexity of the curve. And to account for this convexity, the second order term is also needed. As we'll discuss later in more detail, this convexity always hits the curve positively, whether it's on the downside, it's on the higher side, or on the upside is always higher or above the linear line. And therefore, as you can see with this squared term, H square, it always hits the interest or change in prices positively, but we'll discuss that in more detail. To summarize, in this video, we noted that changes in interest rates have some impact on bond values, depending upon the maturity or horizon of how cash flows are structured on a particular bond. We noted that this property and relationship between interest rates and bond prices can be used as an important risk management measure. We also saw that how we can employ Taylor series in modeling these price changes and using the first order differential or first order derivative of price curve or price function and second order derivative of price function, we can reasonably and adequately model the price change. In this video, we'll compare and contrast and highlight the differences between maturity of a bond and its duration. In the previous discussion, we saw that changes in interest rate had greater impacts on long-term bonds as compared to short-term bonds. However, without understanding and including the cash flow profile, short-term and long-term is just a vague reference. For example, think of a 30-year maturity bond with cash flows evenly spread over time and compare it with a pure discount or zero coupon bond like STRIP. STRIPs are separately traded, registered interest and principal securities. Like we said, STRIPs are special instruments created by stripping the cash flows from treasury instruments. Primary dealers in government markets, they strip out the cash flows of bond and each of the cash flows is traded separately. These are called zero coupon bonds and they have the maturity which can be considered as same as duration. Consider three bonds as provided here. First is a strip with face value or maturity value of 100 and current price 88. Second is a bond with 4% coupon, maturity value of 100 and current price of 111. And third is a approximately 11% coupon bond with the face value of 100 and current price of 152. Now, one of them is strip, the first one, and other two are coupon paying bond with cash flow profile as provided here. Let us examine the time pattern of cash flows. First and foremost, the two coupon paying bonds offer a reasonable or a considerable proportion of their cash flows earlier in time as compared to this strip because there are no coupons with this strip. Bond with 11.25% coupon, the last one, offers a larger proportion of cash flows earlier than maturity as compared to bond with the 4% coupon, this one. Now, if I have to understand the time pattern of the cash flows, I would say the most delayed cash flows appear with this, which is very easy to understand that this bond would have its maturity same as duration, which in this case appears to be 6 years. While for bond second and third, the maturity of 6 years is not exactly same as duration, but if we compare between these two bonds, we can see that a larger proportion of cash flows with third bond come earlier in time, and therefore its duration would be lowest, while that with the 4% coupon bond, it falls somewhere in midway, not as extreme as zero coupon bond, but not as low as the 11%, this 11.25% coupon bond. To conclude, in this video, we noted that maturity may not be same as the duration of a bond. The concept of duration is similar but different from maturity, and maturity is the last cash flow, which is the principle of par value. However, duration should reflect some kind of time weighted cash flow profile including coupon as well as principal payment, and therefore if a bond has higher coupons as compared to another bond with same maturity, its duration is expected to be lower because a higher proportion of cash flows come earlier in time, while the bond with the lower coupon, because its major component of cash flow would then be principal, which comes later in time, is expected to have higher duration. In this video, we'll understand the relationship between bond yield and prices with the help of a simple example. Consider a bond with 6-year maturity and 1,000 principal with 10% coupon, that means $100 or rupee coupon every year. What would happen to the present value of this bond for yields 5%, 7.5, 10, 15, and 20? Chances are that when this bond was issued, interest rate environment in the country was around 10%. That means the yield on this bond was expected to be 10% and it was issued at 10% coupon rate. Therefore, its value would be closer to 1,000, which is face value and principal. However, as the interest rate environment changed, the price would be affected. For example, if the yield was 10%, the discounted present value of all these would result in a value of 1,000, which is the face value or par value. But suppose immediately the yield changes, how do we get the price of this bond? So let's say it suddenly changed from 10% to 5%, although that is hypothetical in nature. But then each of these cash flows would be discounted 1 plus 5% raised to the power 1, which is this, plus 100 upon 1 plus 5% raised to the power 2 plus 100 third year cash flow, which is this, upon 1 plus 5% raised to the power 3. For fourth year, it will be 100 upon plus 5% raised to the power 4. For fifth year, it will be 100 upon 1 plus 5% raised to the power 5. For sixth year, there will be principal plus coupons. So you'll have 1100 upon 1 plus 5% raised to the power 6. Similarly, for different yields, you have to calculate accordingly. So I have already calculated these values. And if you look at these values, an interesting pattern emerges. At 10% yield, the bond has a price which is exactly 1000 or face value. However, if the yields are lower than this 10%, the bond is selling at a premium more than 1000. And if the yield is higher than the coupon rate, the bond sells at discount. The idea is simple here. If the yield is more than coupon, that means the bond is offering you lower coupon than the current risk environment, and this would be reflected in the form of a discount in prices. That means demand would be less and prices would fall. Conversely, if the coupon is more than yield reflects the current return, current interest rate environment in the economy, which is commensurate to the risk of the product. So suppose the yield on the bond is 5%, that means on similar risk instruments like this bond, investors are expecting 5% return, but this bond is offering a higher coupon, so more supply will result in fall in prices like this. Now that we have understood the relationship between yield and price of the bond, it would be interesting to note what would happen to these bonds, for example, this premium bond over the life of this instrument as it approaches maturity, or for these discount bonds as maturity approaches, what would happen or what should happen to the price of these bonds. This we'll examine in the next video. In this video, we'll try to understand the trajectory of bond prices over time as it approaches its maturity. In the context of bond prices and duration, it is important to understand how coupons are structured over time because it affects the cash flows that accrue to investors, and also these cash flows are given certain weight in the duration measure calculation. So how the value of bond changes or behaves as time passes also depends on the nature of cash flows, whether it's a premium bond or a discount bond. For example, consider a pure discount bond like a strip or zero coupon bond with a single cash flow of 1000, which is face value of principal at the end of 5 years. What would be the duration of this bond? Or a bond that pays 50 rupees coupon semi-annually with a face value of 1000, or compare it with a bond that pays 100 with a semi-annual coupon, what would be its duration? We'll try to answer these questions by understanding the trajectory of bond prices over the maturity of its life. In general, there are two components to bond returns that you get. One is a coupon or interest payment, that is interest income, and then capital gains due to change in prices. For now, for simplicity, assume a flat yield curve that interest rates remain constant as time passes. Let's try to examine how bond value changes. To begin with, think of a pure discount bond, zero coupon bond with 3 years to maturity, and the principal or face value to be received at maturity is 1000. Also assume a constant flat yield curve of 10% interest. Now there is 3 years to maturity, so the present value of bond should be, if markets are efficient, around 751.31. After 1 year, again nothing changes. The yield curve remains the same. Face value is 1000, so its present value after 1 year would be 826.45. Now notice there's nothing has happened in terms of risk profile of the bond, only time has passed. The holder of the bond has received a capital gain of how much? 826.45 minus 751.31. This is capital gain due to changes in bond price. If you want to calculate the return, there is no coupon in this bond. So the only return that he gets is this capital appreciation, which is 826 minus 751 upon this, which is 10%. So in last 1 year, he or she has received a 10% return, which was expected because the yield of the bond is also 10%, which has unchanged. So it was easy to understand the changes in bond value over life for a pure discount bond. We noted that for a pure discount bond, if it was a discount bond, the value increases, and if it was a premium bond, the value should ideally decrease and reach to the face value or principal value by the time of maturity. But what about coupon paying bond? Consider three bonds. One is 100 rupee selling at face value because it is offering the coupon rate which are same as the yield of 10%. A discount bond which is offering a lower coupon of 5 rupees as compared to 10% yield, and a premium bond C, which offers a higher coupon than yield and therefore selling at premium. What would happen to them as time passes? Please note all three of them will offer the same amount, exactly 100 rupees at maturity. So if you think of the day of maturity when you are supposed to receive coupon maybe in a half hour or 1 hour, the final principal, not the coupon but the final principal, then at that very instant their prices should be 100. So at the very maturity, very instant when they are supposed to receive their principal, the price should be 100. Now, if you calculate their values at the year end 1, 2, 3 up to maturity, just immediately before the coupon receipt and after coupon receipt, the values are provided here. For example, at the end of year, since this was a bond selling at par value, the end of the year value remains same. Immediately before the coupon payment, the value is 110 because at this stage you are supposed to receive the coupon, And once you receive the coupon, those 10 rupees, the amount goes to your account and the bond value again comes back to 100. And the same happens after year 2 and 3. What about the discount bond? So immediately before the coupon, its value is 96.32, which reflects the value of coupon also. And after you receive the coupon, value falls by 5 rupees immediately after receipt of the coupon. Same for the next second year and third year. But notice a consistent pattern. There is an increase, whether you look at before coupon payment or after coupon payment, there's a secular increase in value. And at the end of maturity, if you look at after values after payment of coupon, immediately after payments of coupon, there's a very secular increase in the value that approaches 100 by the end of maturity. Similarly, for the coupon premium bond, the bond that is selling at premium, immediately before coupon and after payment, there's a decline of 15 rupees, which reflects that the coupon has been received and the value has come down. Notwithstanding that, there's a secular decline in the value. For example, if you just look at the values immediately after coupon payment, the value is 112, then 108, then 104, and approaches 100 by the time maturity. So we can gather from this discussion that if it is a premium bond, then immediately after coupon payment, if you in general, if you exclude the coupon payment, the value of the bond declines for a premium bond, and for a coupon paying discount bond, the value increases. Of course, the movement here is not as gradual. Why? Because in between there is a payment of coupon which causes anomaly, like a sudden decline like this. But if you sort of account for that, then there is a secular decline from this to this. To conclude this discussion, a bond that pays coupon which is lower than yield will sell at a discount, and its value will be lower than the face value or par value, and over the life of the bond the value will increase. That means as time passes it will witness an appreciation in the value, and by the time of this redemption or the maturity time, its value will be same as its principal, or immediately before coupon payment, then it will be same as principal plus coupon. Conversely, when its coupon is higher than the yield, bond will sell at a premium, that's value is higher than the redemption value or face value or par value. As time passes, the value will decline whether you look at pre-coupon payment or after coupon payment, and it will converge to the redemption value at the day of expiry. In this video, we'll provide the motivation behind duration measure as a sensitivity of bond prices to changes in interest rates. Let us recall the typical example that we discussed earlier where the yield was flat at 10%. Suppose there's a sudden shift and the yield increases to 14% for this bond just 3 years ahead of the expiry. The bond had a face value, it was a pure discount bond and it has a face value or par value of 1000. Now we are 3 years in advance, and the present value of this bond can be calculated for 10% yield as 751, a simple discounting process. After the sudden shift, the value suddenly declines more, that is from 751 to this 674, that is after discounting. The decline in value is about 76.34, which is obviously less than the previous value before the increase in yield and after the increase in yield. Compare this to 5 years ahead of expiry. Suppose we discounted this price 5 years ahead of expiry at 10% yield, it was 620, and at 14% yield, this is 519. Notice the decline is much more at 105.55 compared to 76.34. We observe that bond prices are sensitive to changes or shifts in yield curve as we discussed earlier. And we have also provided intuition that duration or time horizon of cash flows has something to do with it. Or in very simple terms, one can consider duration as a measure of sensitivity of bond prices to changes in interest rate. So let us define duration as percentage change in prices divided by percentage change in interest rates. Negative sign here indicates that if yield rises, price falls, and if yield falls, price rises. So we can define duration D as change in price, that is dP naught upon P naught, insert differential form, divided by D of 1 plus I upon 1 plus I. Just remember that D of 1 plus I is same as I. So changes in interest rate is same as changes in 1 plus interest rate. So this is the typical formula for duration measure, which is defined as the sensitivity of bond prices to changes in interest rates. Let us further simplify this notation. So dP upon P naught is percentage change in prices. This can also be considered as return on the bond, which is equal to minus D into D of 1 plus I upon 1 plus I, where D of 1 plus I upon 1 plus I is proportional change in 1 plus I, something similar to here prices, which is proportional change in prices. This can be thought of as proportional change in interest rate 1 plus I form, where I is the current interest rate, D is the duration, R is the return due to changes in interest rate or percentage change in bond value. Now we can further simplify this notation using D upon 1 plus I as dA, where dA is called the modified duration, which is D upon 1 plus I. dA equal to d upon 1 plus I. Also, please note d of 1 plus I changes in 1 plus I is also same as di. So I can write this as dA and d of 1 plus I as I. So return equal to minus dA into di. So if there are small changes in interest rate, one can multiply it with the modified duration dA, which is this. You can get percentage change in bond price, or in other words, returns. And the negative sign here indicates that when interest rate rise, prices fall, and vice versa. To summarize, in this video, we introduced duration as a measure of sensitivity of bond prices to changes in interest rate. We also noted that if one converts the simple duration to modified duration form 1 plus I, which is equal to dA, one can directly multiply this modified duration with changes in interest rate for small changes in interest rate to compute the percentage changes in bond prices or bond returns. In this video, we'll provide a simple proof and exposition of duration measure. We'll start with a very simple pure discount bond to understand the concept of bond duration. This pure discount bond has a current price of P naught, and this is at the time of purchase, and a single cash flow of 1000 at maturity, that is par value or face value. So by simple rule of discounting, P naught will be equal to 1000 upon 1 plus I raised per T. Now let's differentiate this with respect to 1 plus I. Recall we are considering changes in 1 plus I. So dP naught equal to 1000 into 1 plus I raised to the power minus T plus I, because we are differentiating this expression, and minus T d of 1 plus I. So we are considering changes in the form of d of 1 plus I. So dP naught becomes this and P naught is this. So I can simply replace this 1000 upon plus I raised power T as P naught, which will take us to this very simple notation. Now recall our definition of duration. We said our definition of duration was dP naught upon P naught equal to minus T into d of 1 plus I upon 1 plus I, which means that T here is same as D. Or in other words, the duration of a pure discount bond is same as maturity, as we already had that intuition. Which also means that if there's a 5-year pure discount bond and there's a change in interest rate, for example, 1% change. Now here we are defining change as d of 1 plus I upon 1 plus I. So 1% change in interest rate, the price should change by 5%, or the return on the bond should be 5% positive or negative, depending on whether yield falls or rises. Now let us arrive at the expression for coupon paying bonds. For a typical coupon paying bond, the pricing expression can be written in the form of discounted cash flows. We have made it more generic. So for example, coupon can be different. The last CT may include principal and coupon, and so on. Any generic expression is okay. So we differentiate with respect to d of 1 plus I. And again, we are talking about changes in 1 plus I. So dP not equal to NC is minus C1 upon 1 plus I raised to power 2 minus 2 times C2 upon 1 plus I raised to power 3. This is a simple differential of the expression. Now, both the sides we can divide by P naught here. And now if you recall our typical definition of duration, it was dP naught upon P naught equal to minus D into D of 1 plus I upon 1 plus I. If we compare this expression here, we need to take 1 plus I out, and we are left with this expression of duration. 1 plus I we have taken out. So this becomes the typical expression of duration, that is this. So from here we get our definition of duration, where duration can be defined as 1 into C1 upon 1 plus I raised to power 1, and so on, which can also be written as notation summation, more compact notation of summation, sigma t equal to 1 to t into ct upon plus I raised to power t upon p naught. Now this has a very important economic implication also. Even if you do not like to remember or learn the mathematics of it, you understand that here we are typically multiplying time, we are assigning weights to times. And these weights are nothing but present value of cash flow. See, P naught is the present value of all the cash flows received together. For any given cash flow, we are looking at its time T and taking its weight as a proportion of that cash flow to the overall bond price. So it is time weighted T into W1 T plus T2 into W2 and so on, where each time is multiplied by weights, which is nothing but proportion of cash flow. So we are time weighted cash flow. So these are cash flows weighted by time to arrive at the duration of bond, which seems to be rather more intuitive. To summarize, in this video, we derived duration with a simple proof for a pure discount bond and coupon paying bond. The resulting expression suggested that duration is simply the time weighing cash flows, that is, cash flows are used as weight and multiplied to their times to arrive at the duration of the bond. In this video, we'll understand the concept of duration with the help of a simple example. Consider a 10-year bond with 14% coupon and 10% interest rates with annual coupon payments. So frequency is annual. In order to compute the duration, the first step is to compute the prices P naught. Please note, because the coupon is 14% and the interest rates are 10, so every coupon will be discounted at appropriate discount rate. For example, the first coupon is discounted by 1 plus 0.1, and the last coupon is discounted by 1.1 raised to power 10, and also the principal payment that is there. So this 1.14 reflects appropriately scaled principal and coupon payment. For example, if coupon is 14%, principal is 100, then 140. Similarly, if coupon is 14%, principal is 1000, then it would be 1140. The next step in calculation of duration is to weigh the times with the appropriate cash flow. So for example, now that you have P naught, you have to calculate the present value of each cash flow. For example, first cash flow is C1 upon 1 plus 1 raised to power 1 divided by P naught to get the appropriate weight which needs to be multiplied or given to cash flow number 1. Similarly, for second cash flow, C2 appropriately adjusted C2 upon 1 plus I raised to power 2 divided by P naught multiplied by 2 and so on. The final Tth cash flow, which is the last 10th year, which includes principal and coupon, you discount it 1 plus I raised to power t divided by P naught and multiplied by t to get the duration. So let's see, we have P naught, we discount all the cash flows appropriately to get a price of 1.246. Note that this is a scale price. So in case 1000 rupee worth of bond, it will be 1246. For 100 rupee bond, it will be 124.6. Now the bond is selling as premium precisely because it is offering a coupon which is higher than interest rates. The next step is to multiply each present value of each cash flow scaled by the price, divide by price, this factor, and multiplied with the time. So the time is weighted with the appropriately scaled cash flows. We get 6.36. Now, because the frequency of this bond is annual, these are annual coupon payments, payments are annual, we can straight away say that duration is 6.36 years. And why this is lower than 10 year? Because a substantial amount of cash flow in the form of coupons are coming earlier in time than the principal or maturity date. In this video, we'll try to understand the factors affecting duration. The duration of bond predominantly depends on three factors. One, nature of cash flow and their profile, maturity, and interest rates. Note that let's say this bond has a maturity of 10 years. However, the duration is much less than that. This is quite intuitive because a sizable portion of cash flows are received as a part of coupon in the initial years. What happens when you decrease the coupon? In that case, the principal or face value that received at the end of the maturity becomes larger and larger as a share of the overall value. Since it is received at maturity at the last, the duration increases. So a higher duration would be observed. Similarly, if you increase the coupons, a larger portion of bond value that in the form of coupons will be received earlier in time and a lower duration would be observed. Next, what about changes in interest rates? Suppose interest rates have increased, the highest impact of increase in interest rate or decrease in interest rate is observed on the principal amount or later cash flows, the coupons that come later, including the principal amount. So increasing interest rates would relatively decrease their value to the overall bond value and thereby decreasing the duration measure. Conversely, if interest rates are decreased, then in that case, cash flows that are coming later, like principal and coupon that are coming later, will have a relatively higher value in the total composition of bond value, and therefore duration will be higher. Lastly, ceteris paribus, everything else remaining the same, higher the maturity, greater the duration. For example, think of two pure discount bond. One is having 10-year maturity and one is having 5-year maturity. The 10-year bond obviously will have a higher duration. Or two bonds having same coupon rates, one having 20-year maturity, one having 15-year maturity. 20-year maturity bond will obviously have a higher duration. In this video, we'll try to understand duration as a measure of price value basis point and also the intuition for convexity. Let us start with a simple example. Consider a bond with profile 8.5% coupon and 100 principal or face value to be received at maturity. So this 8.5 is received for 4 years, and in the final year in maturity, you will also receive the face value or par value. So the total value received in fourth year is 108.5. Let us first calculate its present value, that is 8.252, the coupon first year, second year coupon present value, third year, and so forth, so on and so forth. The final year coupon and principal payment present value of 96.41. Using this information, we can calculate its duration. So for example, I can divide this value by the total price to get the weight for year 1 Weight for year 2 can be similarly calculated. You can see the weight for year 4 is highest because it includes the principal payment as well. Now these weights will be multiplied with the time, corresponding time. So 1 will be multiplied by this, 2 will be multiplied by this, 3 with this, 4th with this. So you'll get time weighted amounts, time into weights being the proportionate cash flows. If you add them all up, and because the frequency or compounding frequency is assumed to be annual, the summation simply result in duration of the bond. So the duration of the bond is 3.6 years as we have calculated. Now we'll also understand what is the change in this bond price for 1 basis point change in interest rate. We'll assign half basis point up and half basis point down. That means 3.005%, half basis point up and half basis point down, resulting in 2.995%. This means a total change of 1 basis points. Now, as per the duration measure, this change should be captured by dp naught by p naught, which is the percentage change in price. We are considering here a change of 1 basis point, which is 0.01%, and by definition, it should be minus d into d of 1 plus I, which is di itself, upon 1 plus I. So this should also give us the percentage change. Parallelly, we also calculate the corresponding present values for these percentage points. So at 3.005%, what is the value of this coupon, and so on. Similarly, at 2.995%, what is the value of this present value of this coupon, present value of this coupon, present value of this coupon, and present value of principal plus coupon payment. So that is a slight decrease. You can see there's a slight decrease in prices due to this half basis point increase in interest rates, and a slight increase in price due to decrease in interest rates. So the interest rate decrease results increase in prices. And we'll try to see if this matches with the duration measure calculation, the price change calculation as per duration measure. Please note that because duration of this bond is 3.6, we can calculate that minus d into d of 1 plus I upon 1 plus I, which is 3.6 upon 1 plus 3% into 0.01% as 0.035%. Now we need to know whether this up change and down change exactly matches this amount. So what we do is we calculate from this down change and up change, which works out to 0.0175% both sides. So if we add them up, we get a change of 0.035%, which is same as this. There's another way. You can also calculate a price change from this to this minus this, divided by this, which will also result in 0.035%. So this minus this divided by this price change is also 0.035%. This is an interesting point. What this suggests is that our duration measure for small changes such as 1 basis points reflects the percentage change in bond price. That is precisely 1 basis point change in bond price is captured by our duration measure. So that is why duration measure is also considered as price value basis point measure. Also, one important point that I would like us to remember for subsequent discussion is that these changes are quite symmetric. That is, same changes up and down movements. So whether I go on the downside or upside, the changes are almost identical. But if I change the interest rate by a larger amount, say 1%, that means half percent up and half percent down, does this identity or rule remains, or is it violated? Let us see. So we'll start with the half basis point change up and down, which means if I look at half basis point, it should be 1.7476, which is close to 1.75%. Whether you look at up or down, the duration measure predicts a change in bond price, same price change up and down. Let us calculate that. So if you consider a change due to increase in interest rates, these are the price present value, this is the price, and these are the price for a decrease in interest rates. You can see with increase in interest rate, the price has declined. With increase interest rate, the price has inclined. With decrease in interest rate, price has risen. The changes are not identical. You can see when it comes to increase in interest rate, the change is rather small as compared to this. And when it comes to decrease in interest rate, change is rather large as compared to this. So 1.7476 is smaller than this 1.767. What does it indicate? Also, another interesting point that we need to remember, if you add up this thing, the overall change is quite same. The overall change, if you look at the overall change, that means 122.572 minus 118.365 upon 120.44. The overall change is identical. What it means, there is some delta in this change that is subtracted when the prices go low and added when the price go up. So when we add this up, the overall change is almost same as that predicted by duration. This delta is precisely what we call as convexity correction. We correct it with the help of convexity. So as you can see, the overall change is same. The decline is less by a certain delta, while increase is more by a certain delta, which we are calling as convexity correction. Just to give you some intuition, what happens exactly is that if you look at the movement of bond prices over changes in interest rate, they appear something like this. Now, over small changes, it is linear, like 1 basis point change, which we could predict using only duration. However, for large changes like this, the rise is more by this delta, while the fall is less. So you can see when the bond prices fall, as per that predicted by linear line, this linear relationship, it is not as much as this predicted by this linear line. It is rather less by this delta amount, while the rise is rather more. So as predicted by this linear, from here to here, the rise is slightly higher by this delta. This delta is precisely the convexity correction that we are going to discuss. To summarize, in this video, we learned that changes in bond prices can be rather accurately predicted by duration over small ranges, but like 1 basis points, and that is why duration is also referred to as price value of basis point. However, over large ranges, there is small correction needs to be made, which we are going to discuss in the next video. In this video, we'll introduce the concept of convexity correction. From the previous video, we got the intuition that duration works well for small movement in interest rate. That means it works well in predicting price changes for small movement of interest rate. But for larger movements, duration has some problems. From the Taylor series, we know that the price change or return, that is percentage change, dP by P, are proportional to percentage changes in interest rate, which is d of 1 plus I upon 1 plus I, only for smaller changes in interest rates. For large changes, one needs to add a small correction term called convexity. Let's see why. Let us look at this diagram of yield or interest rate changes with price. Think of this point P naught where we are standing. Due to changes in interest rates or yield on either side, price moves up or down. For a decline in yield, for smaller changes like this, or increase in yield for smaller changes like this, the linear assumption, the linearity that changes are linear, almost holds with this curvature. So this convex kind of curvature almost matches the linear relationship. However, for larger changes, for example, if you look at larger changes, if you move along the linear line, the curvature moves slightly up. That means increase is more, this delta increases more for up movement. While at the same time, if yield increases and you look at the movement downside on the linear curve, the decrease is less. The delta is slightly less. So this delta is slightly less than that predicted by linear line. This is the intuition behind convexity correction. In order to make more precise prediction for price changes over long or large changes of interest rates or larger sort of increments, you need to add or subtract this convexity correction in prices. Let us go back to our original duration formula where the assumption was that price changes, percentage changes in price dP naught upon P naught, are proportionately related to percentage changes in interest rate with the constant being D. Or in other words, D is the percentage change in price divided by percentage change in interest rate in the 1 plus I form with a minus sign. We also define modified duration D modified as 1 upon Pi into dPi upon Di. Or in other words, D modified is D upon 1 plus I. To put it otherwise, your D upon 1 plus I, D upon 1 plus I is nothing but D of Pi, this one, upon Pi upon Di. This is also same as D of 1 plus I, this one. Now, we also know that this dpi upon pi we can write as minus d into d of 1 plus I upon 1 plus I. In the form of d modified, it becomes d modified into d of 1 plus I. So this was the typical relationship of price changes dpi upon pi with d modified into di that we already know. Let us define convexity in a parallel manner with duration. Recall, we said d modified was dpi upon di into 1 is 1 upon pi. In a similar manner, define C modified, convexity modified as 1 upon pi into d square pi upon di square. So the second differential. Now, similar to d modified equal to d upon 1 plus I, we define C modified as C convexity upon 1 plus I raised to the power 2. That is, convexity upon 1 plus I raised to the power 2 is this term 1 upon pi into d square pi upon di square, or rather convexity equal to 1 upon pi into double derivative of pi with respect to I into 1 plus I raised to power 2. So this formula matches with the duration formula, which was this. So there are parallels between convexity and duration, wherein convexity sort of captures the second differential and gets associated with 1 plus I raised to power 2 here. To summarize this discussion, we know that price is not exactly a linear function of interest rates. The convexity precisely captures this aspect of the price change, that is the extra incremental change on account of non-linear nature of the relationship. And convexity here is defined as 1 upon pi into second derivative of p with respect to I into 1 plus I raised to the power 2. In the next video, we'll try to find the simple proof of this relationship. In this video, we'll have a look at simple proof about convexity correction. To begin with, recall the Taylor's approximation for small changes. For example, consider a small change of di pi plus h equal to pi plus first derivative of price into h, then 1 by 2 times second differential of price into h square, and so on. Now, over small ranges, you need not go any further, and you can simply consider the change in price as first differential into change h, where h is small changes in interest rate, and 1 by 2 times double differential of price into h square. Let's take it further. In this expression, as we said, h is the small change in interest rate, and there are two components to this change in price. Price assumed here as a constant function of interest rate. First component comes from the duration part, or the first differential of price multiplied by the change in interest rate, and the second component comes the second differential of price multiplied by h square. Now, we have already seen that first differential p dash I equal to dpi by di, which was defined by this formula. This was the first differential. Likewise, we can define second differential as d square pi by di square. Now here it was 1 plus I raised to the power t plus 1, so it will become t plus 2, which is this, and 1 minus symbol, so minus symbol will be cancelled. Also, you will have t into t plus 1 overall. So this is your typical second differential, which we are going to make use of. Let us settle this first component because we are very familiar with this. In the first component, we are saying that this price change, and we'll divide the overall expression with pi. So now you'll see where we are going with this. So we'll divide the entire expression with pi, and recall our typical definition of duration. We defined our duration as percentage change in prices divided by percentage change in interest rate in this form, d of 1 plus I, although d of 1 plus I is also same as di, as we said, but we define duration as percentage change in prices divided by percentage change in interest rate. Negative sign was customary because when yield increases, prices fall. Now here the value p dash I is nothing but dpi by di, and h is again small change in price, so di. So this will result in dpi by pi, and therefore p dash I h upon pi is equivalent to this identity. So I can replace this p dash I h upon pi as simply the duration form here. So the first component is well settled. Here we need to remember that h is small change in interest rate like di or d of 1 plus I. So this takes us to the first component, which can be written like minus d into d of 1 plus I upon 1 plus I. Now let's look at the second term, which is 1 by 2 times second differential of p into h square divided by pi. Recall, we already defined convexity in very simple manner as p second differential into 1 plus I raised to the power 2 upon pi. This was the typical definition of pi, which we saw in the previous video, which we can also write as convexity upon 1 plus I raised to the power 2, which is equal to double differential upon pi. Again, h is small changes in interest rates. Now, this gives us the logic that we can replace this second part, this part p double dash I upon pi, from convexity upon 1 plus I raised to power 2, which means this overall expression becomes 1 by 2 times convexity, this 1 plus I raised to power 2 into d of 1 plus I raised to the power 2, because of this h square. H square will be d of, so recall h can be written as di or d of 1 plus I. So h square will be d of 1 plus I raised to power 2. This is our overall price change formula with addition of convexity correction. Now, in this resulting formula that we just saw, We have proved in the previous step that second differential of pi was this 1 plus I raised to t plus 2. So this was the 2 and t into t plus 1. The negative sign converted to positive because of the second differential. So this is your definition of second differential of pi. And therefore, C convexity, which was speed second differential into 1 plus I raised to 2 upon pi, can also be written, because this 1 plus I raised to 2 will cancel out. It will be also written in this form. So we know how to calculate convexity also. And duration we already knew can be calculated using this formula. So using convexity and duration from these formulas, substituting the values, one can calculate the percentage change in prices over reasonably large ranges. Like for example, if you look at RBI, it changes interest rate by 25 to 50 basis points. A fairly accurate measure into changes in bond prices can be estimated with the duration and convexity correction with this formula. In the next video, we'll try to understand the entire thing with the help of a simple numerical example. In this video, we'll try to understand the role of convexity with the help of a simple example. Consider a 5-year pure discount bond that pays a par value of 1000 at the end of maturity. Because it's a pure discount bond, there are no coupons in between. The current interest rate or yield is 10%, and assume that suddenly the interest rate changes to 12.2% or the yield changes to 12.2%. Now, because of this rise, price should fall. What should be the return to bondholders from the change in this price, or what should be the percentage change in price due to this? So, P naught, as per this, one need to calculate P naught, then P1. P1 is the revised price. Then you need to calculate the percentage change through P1 minus P naught upon P naught. Now, the duration of bond is 5 years, so it's because it's a pure discount bond. You also need to calculate the percentage change in interest rates in the 1 plus I fashion. So d of 1 plus I upon 1 plus I percentage change interest, and then compare whether this change and the change predicted by duration measure, does it match or there is a gap. So let's do that. So first we calculate P naught, which is 1000 upon 1.1 raised to 5 discounted for 5 year. Now there is a sudden change and interest changes to 12.2%. So the discounting factor changes to this, and you have resulting price as 562. Now you can see earlier the price was 620.9 and suddenly there is a decline. So the overall percentage change, if one has to calculate, it is negative and 9.4%. The negative sign reflects increase in yield. Let us use our duration measure to predict this change. So our duration was 5 and percentage change in 5 is 0.02. So we can calculate 5 into this percentage change of 0.02 to get a overall change of 10%. Now notice this increase or this change predicted by duration is rather higher in terms of magnitude than this actual change. This difference is basically on account of the convexity of the change in price, for which we need to do the convexity correction. Now, to calculate convexity, recall this was the formula. And once you calculate the convexity, in order to predict the change on account of convexity, you need to multiply 1 by 2 into convexity into d of 1 plus I raised to 2 divided by 1 plus I raised to 2. So let us see. So convexity we calculate using 1 by 2 into t plus 1, which is 5 into 5 plus 1. Because there is only one single cash flow, it is 1000 upon 1.1 raised to 5 divided by 620. Now please note here pi would be this, because we are predicting change from this starting point, and convexity works out to 30. So if you multiply 1 by 2 into convexity into 1 plus I raised to 2, this becomes 0.6%. So this is the d of 1 plus I upon 1 plus I raised to the power 2 part, this one. So it becomes 0.6%. Now, if we add the changes on account of duration, d into this 0.02 and convexity this, we are able to reach that 9.4% change. That means that when your yield rises, the duration predicts the change as this. However, there is extra delta because of this convexity of the curve, which is accounted for this 0.6%, which you add to this 10%. It results in a slightly lower decline. Now, please note this convexity always benefits the price movement. That means it is always positive. And to our satisfaction, the convexity measure has improved the efficiency of our price change estimation, which is more closer to the actual price change, which is this. In this video, we'll summarize our discussion on convexity correction. The idea behind convexity is rather simple. If you examine the relationship between bond price changes and interest rate shifts, so on x-axis if you have interest rate shifts and on y-axis if you have price changes, the convexity behavior would result in a price changes like this in the form of a curvature. Now, the way duration works, it only predicts linear changes, changes in a linear manner. So when your change in interest is rather small or small ranges, the change predicted by this linear measure, that is duration, and the actual price movement are almost similar. So there's no problem. However, when the changes are rather large, like 25 to 50 basis point or like half percentage changes like this curvature affects, and you can see the way it affects the price changes are not similar to the linear movement. So for example, if there is an interest rate decline and rise in price, then the duration measure with its linear capabilities would measure this price change, while actual price change would be little more higher by a certain delta amount. Similarly, when interest rates are increasing, the linear measure, that is duration, would predict price changes that are rather more decline as compared to this curvature, which says there is a decline but relatively less than this linear measure. Again, by the same delta. The same delta is called convexity measure, which benefits the owner of the bond, holder of the bond. Either ways, when there is an increase in prices due to decrease in interest rate, it benefits the bond owner by increasing the price more, while when there is a increase in interest rate and decline in prices, the decline is rather less, and this convexity again benefits the bond owner. In this video, we'll discuss management of bond portfolios. We have discussed that changes in interest rates affect bond prices, and these changes are something similar to somewhat systematic risk. For example, we discussed for equity portfolios, systematic risk is an important factor. Similarly, for bond prices, interest rate changes act as a systematic risk, as in they affect large number of bonds in a similar manner. So there are techniques to increase the immunity of bond portfolios against these changes in interest rates. These include predominantly exact matching and immunization. Let's discuss them one by one. So in case of exact matching strategy, or called dedication, you try to match almost exactly the inflows and outflows, your liability with your assets. For example, suppose given these profiles, the liability profile is given and you have two bonds A and B available, their principal and coupon payments. How do you neutralize your position by matching bond A and bond B? If you notice, bond A exactly matches your liabilities. Therefore, it would completely neutralize your interest rate risk. Also, if you look at bond B, let's say bond A is not available, but even bond B does a reasonable job. So you get 198, out of which 100 would be used in repayment. The remaining 98 can be put in bank. Next year, if as long as it is more than 100, it can meet your repayment obligations in 2, and 3 is also hedged. So bond B also does a reasonable job. In this video, we'll discuss immunization or duration matching strategy. In the previous video, we discussed that one can match the cash flows of assets and liabilities to make your portfolio less sensitive to interest rate changes. However, in practice, it is very difficult to find the bond portfolios that exactly replicate your liabilities and their cash flows. In that case, theory suggests that application of duration measure is very useful, because duration measure precisely captures the sensitivity of a bond to interest rate changes. So if two portfolios are duration matched, chances are these two bond portfolios have similar sensitivity to interest rate changes, and this kind of immunization strategy aims to meet the duration of liabilities to that of assets. So match the duration of liabilities to the assets, and in turn, the sensitivity of the overall portfolio to interest rate changes would be very less. While a more perfectionist fund manager may like to not only match the duration of the bond portfolio but the convexity as well. However, it's very difficult to match both the duration and convexity aspects. For practical purposes, literature suggests that duration matching does a reasonable job of making your bond portfolio less sensitive to interest rate changes. If the two portfolios of similar size are duration matched, changes in portfolio on account of interest rates will be quite similar. Also, the duration of a bond portfolio is simply weighted average duration of individual bonds, where the weights are proportionate amount invested in individual bonds. The simple formula is DP, portfolio duration, is weighted average, X size being weights multiplied by respective durations. Now, under the umbrella of immunization, a large number of strategies are there. For example, if you have a portfolio with duration 10 years and its duration is matched by a portfolio of 9-year and 11-year bonds invested in equal proportion, this is one strategy. This strategy is called focus strategy, when the constituents of the portfolio are very close to the bond immunized. The another strategy is if you invest in 5-year and 15-year kind of duration bonds, their overall duration is also similar to the maturity of 10-year bond. And this kind of strategy is called barbell strategy. Now the question is whether these are active or passive strategies, and that question is to be answered knowing that whether duration changes with the yield. To answer this question, we need to understand that immunization is not exactly a passive strategy as it may sound. The reason being, if you hold your bond, you identify and hold your bond till maturity, interest rate changes also result in duration changes of the bonds, because these cash flows, the rate at they are discounted, change, and duration was calculated at a certain yield curve, at a certain interest rate. So if those interest rates change, the duration of the bond also change. And in that case, your duration of asset and liabilities may not remain the same as the interest rates change. Therefore, a restructuring would be required. And in that process, this immunization becomes a more active strategy where you have to dynamically match your asset and liability durations period after period. In this video, we'll introduce a few passive bond management strategies. Indexation is a very simple and straightforward passive bond fund management strategy. The idea here is that in one index, there can be large number of bonds in a theoretical index. Therefore, you cannot exactly hold all the bonds in your bond fund portfolio. So what fund managers do, they follow something called cell matching. For example, a particular bond fund index can be broadly categorized under different buckets or parameters. For example, what is the proportion of corporate bonds, government bonds, and so on? What proportions of rating categories, for example, AAA, triple B, double B, and so on. Lastly, you can also think of in terms of duration, what is the duration of different bonds. Now, once these buckets are identified or these parameters are identified, you can select bond to meet the overall profile of that index under these parameters. So while the number of bonds may be much less, but still you are able to replicate the bond portfolio profile around these parameters. Now that these buckets of parameters are identified, you can select bonds to meet the profile of these buckets rather than exactly matching the bond fund index bond by bond. For example, if you have multiple cells that characterize your bond fund index, a particular cell can be matched by considering, let's say you can make the following statement. What proportion of the overall original index is invested into corporate bonds rated triple B with a duration of 4 to 6 years and a coupon rate of 5 to 8%. So this kind of description can be added to different cells based on your overall parameter buckets. You can match cells similarly. The more closer you are to your bond fund index, the more closely you track. Now, this kind of description, you can create various cells, and like we said, you can match your fund with the original bond index. And generally, it has been observed that this kind of cell matching is highly efficient in replicating of original bond performance. In this video, we'll discuss active bond fund management strategies. To begin with, broadly, we can classify them into four types of strategies. One is aggregate interest rate forecasting, sector selection, sector rotation, and individual bond selection. As per the aggregate interest rate forecasting strategy, investment managers and fund managers that are handling bond, they try to forecast the term structure of spot rates, for example. This also affects bond yields, so saying that forecasting term structure is same as forecasting bond yields as well. Now, if the expected interest rate rise more than what market anticipates, then you can shorten the duration of your bond portfolio to benefit from the excess rise. So in general, bonds will fall, but because you have shortened the duration, your fall will be less. Conversely, if you expect that the fall in interest rate is more than what is anticipated, you can increase the duration and then your portfolio will rise more than other competitive portfolios. However, there are two important points here. First, you have to accurately forecast the interest rate. That means the movement of interest rate should be according to your prediction, and also you have to predict earlier and more in advance than market. So your forecast has to be different and accurate from market. For example, whatever market forecast is, that will be already reflected in the current prices. So if market believes that interest rates will rise by 5%, the price of bond will fall to reflect this rise. Only and only if you predict that this rise will be more than 5%, say 7, 8, 9, 10%, and then that happens as well, and you predict it much better and earlier than market, then you can expect a further fall, a more decline than what market anticipated. And in that case, you can decrease the duration by selling the long duration bonds and buy the short duration bonds. Now that you have short duration bonds in your portfolio, the effect of rising interest rate will be much less. And a vice versa strategy can be thought of in case of fall in interest rates. Another strategy is sector selection. So for example, as the name suggests, you can pick undervalued sector that are expected to do well in future, or pick overvalued sector that are expected to perform badly in future, but you have to do it, like we said earlier, better than market and earlier than market. Next strategy is very similar, which is individual bond selection. You can select those bonds that are either overvalued and undervalued as per the current term structure spot rates. Again, this overvaluation and undervaluation, to be accurate, you have to make your forecasts of interest rates earlier and better than market. Another strategy is sector rotation. That means shifting your portfolio's relatively higher weight in one sector as compared to other, depending upon their relative under or overpricing. For example, you may forecast again earlier and better than market that one sector will perform better than another sector in a relative manner. For example, let's suppose you believe there are triple rated private corporate bonds and government debt. Now, you may believe that market has probably overreacted to the risk of these AAA rated corporate bonds, and therefore they are offering a higher interest rate as compared to AAA rated government bonds. So you can increase the weightage in your portfolio for these AAA rated private securities and sell some of the government debt. When the adjustment takes place and you have made some higher returns, larger abnormal returns, then you can revert back to your original positions in the bond portfolio. Let us summarize this lesson. Bond prices decline with interest rate increases and rise with decreases. A bond that offers higher coupon sells at premium, and over the life of the bond, the value declines and converges to face value of the bond around maturity. This sensitivity of bond prices to changes in interest rates is determined by the duration of bond. While duration appears to be similar to the concept of maturity, they are not exactly the same. Duration depends on the cash flow profile and term structure of interest rates. It is the present value of weighted average of time of bond cash flows. Everything else remaining the same, a larger maturity results in higher duration, large coupon results in lower duration, and higher interest rates lower the duration. Typically, the impact of interest rate rise and fall are not symmetric on bond prices. This is due to the convex nature of the relationship between bond price and interest rates. While the duration measure only works for small changes, as it considers the bond price and interest rate relationship to be linear in nature, this requires a convexity correction. This correction affects both rise and fall in prices in a positive manner, so that fall is less and rise is more. The two important bond portfolio management strategies are exact matching of cash flows and immunization. The immunization strategies require matching duration and convexity to decrease the sensitivity of bond prices to interest rates. Passive bond portfolio management strategies include indexation, and active strategies include interest rate forecasting, sector selection and rotation, individual bond selection, among others.